Liberty University Vanguard project submission for the Mars Society University Rover Challenge.
The communication system for the rover is broken down into two main sections: video transmission from the rover to the base station, and a two-way channel for transmitting commands to the rover and receiving data from the rover. The video transmission will be accomplished using a commercially available video transmitter and receiver, such as the ones used for FPV drones. The two-way control channel will be implemented using a custom radio designed and built by our team. We will be using frequency shift keying to modulate binary data onto the carrier wave, allowing us to directly transmit commands from the base station microcontroller to the microcontroller on the rover. To ensure our signal has sufficient range, we will design the FSK modules to operate using amateur radio frequencies, preferably between 144 and 148 MHz or 420 to 450 MHz. Since multiple of our team members hold amateur radio licenses, using amateur frequencies is an acceptable option that should give us increased transmit range and reliability. The programming team has worked closely with the electronics team to design the electronics in a very modular fashion. This allows changes to the electronic subsystem of the rover if needed without significant changes in the code. The system is broken down into one master and several subsystems, with each subsystem handling all of the details which are abstracted from the master. The subsystems will then interface directly with the sensors and motors, allowing the master to solely focus on the task of controlling the entire rover as a singular system, with the master subsystem communication taking place through an abstracted interface. The mechanical system uses a partial rocker bogie leg system that is attached to an 80-20 aluminum extrusion frame. The motors and gearboxes are then bolted directly to the legs, allowing us to keep the highly inductive motors away from the more sensitive electrical equipment in the main body. Each motor weighs 4.5 pounds with a 3.5-pound gearbox and a 2-pound tire system. Using 6 legs, this allows us to keep over 60% of the total weight in the bottom one-third of the rover. The tire system is designed using off-the-shelf tires that were designed for electric mini motorcycles, allowing us to obtain high-performance tires at low cost. They were then split in half and notched to fit around an aluminum spoke and then filled with an open-cell foam for added rigidity and to keep the tires from filling with rocks. The result was high traction, low cost, and low weight. The arm was then mounted on a Lazy Susan bearing with 2 arm segments, allowing it to reach down to the ground and up to a height of 1.5 meters.
The primary design consideration when evaluating the rover design was that it must be modular, reliable, and functional. The primary design choices for the power distribution and computational systems were driven by the need to compartmentalize the design across an entire team. This allows us to have multiple people work in parallel. Secondary to this, we stressed reliability, choosing components that are either designed for extreme conditions, certified for use on the International Space Station, or derating components far under their rated capacity. The operating voltage of approximately 21 volts allows for efficient power regulation, but also the power required by the drive system. Our drive system consists of 6 250-watt electric motors and pulls about 9 amps at minimum power and about 60 amp at full power. Our battery system is capable of 100 amps per battery at 5.5 amp hour. We also plan to run 6 batteries in parallel for maximum runtime. Our motor controllers are automotive grade and certified for extreme environments and mechanical strain on the die of the chip. They also include overvoltage, overcurrent, and overtemperature protection. The science plan for the rover is to switch out our main hand on the rover for a special spade scoop shovel outfitted with a container for holding soil, and a LiDAR sensor to test for proper depth. Candidate locations for soil sampling will be found by taking atmospheric readings for carbon dioxide, temperature, humidity, and radiation. After determining a suitable location, we dig down and collect a sample and place it into individual soil containers that will be inside the testing unit on the rover. This whole science unit can then be sealed off to prevent cross-contamination. Once in the containers, we can run the onboard tests for radiation, pH, and moisture. Because these tests don't contaminate the soil, we have clean samples for base station testing where we can run more intensive tests.